Okay, so we just talked about probability of simple events. And I kind of just briefly stated in there that our probability of simple events occurs from, our probability of simple events take place, and we used numbers. And when we used numbers, it created what was considered like a theoretical probability. Okay? Theoretical comes from which root word, guys? Those of you that are good with that kind of stuff. Theory. In theory. So in theory, right, if you flip a coin, okay, choosing heads, right, we just did this, choosing heads, there's two different possibilities, heads or tails. You have a 1 in 2 chance in theory, all right, by looking at the sides and by looking at favorable outcomes. That's what we were talking about, okay? However, there is another probability that comes about from playing these games, and that is when we're actually playing it out. It's with what's called experimental probability. So what do you think experimental comes from? Experiment, right? Experiment, actually doing it, right? If you're doing a science project and you have an experiment, I mean, you do a bunch of stuff about the experiment, but when you actually do the actual experiment, you're actually doing whatever, your project's about. So that's what this is all about. So we're going to be talking about those two different types. We're going to talk about theoretical and experimental, and we'll talk a little bit about comparing and contrasting the two of them. All right, so similarities, differences. All right, so with your vocab, all right, our very first word is uniform probability model. Everyone? Okay, so the definition in your book says this, it says a probability model which assigns equal probability to all outcomes. Equal probability to all outcomes. Okay, so this we're just talking about this, and that has like a little pie, right, with a little plus sign, a circle with a plus sign in it. But bottom line is that each section is equal size. That's what that basically means. The uniform probability model. We were talking about it in the last lesson, right? What was it, like cat and dog? I made the little sliver for a dog. Okay. For the probability, at least theoretical, to work, okay, it's assigning, okay, each equal probability to all outcomes. And that's just a little picture to show it. All right. So here's what we were just talking about: theoretical probability. Everyone. Okay, and this is, your book says it's the ratio of the number of ways an event can occur to the number of possible outcomes. Okay, here's what's really important in this definition. It is based on what should happen when conducting a probability experiment. It's based on what should happen, based on the number of possible outcomes and the number of favorable outcomes. Okay, in your little note section there on the right little box. So, for example, when you're flipping a coin, probability of flipping heads would be what we talked about a second ago, right? 1 out of 2. 50% chance. However, what we're really going to talk about that's new in this lesson is the experimental probability. Everyone? Okay, let's try that one more time. Experimental probability. Everyone? All right, and this is an estimated probability based on a relative frequency of positive outcomes occurring during an experiment. Okay, so you're doing an experiment. You could use tally marks for the frequency of what's happening. Okay, but this next part is what's important. It is based on what actually occurs, right? Oops, sorry. What actually occurred during the experiment. Not what should occur, but what actually occurred. So, for example, when you're actually flipping that coin, because that's the experiment, the probability of flipping heads, you could have flipped the coin 50 times and heads came up not 25 times, which would be half of the time, came up 31 times. 31 out of the 50 times. So that's not, it's more than 50%. It's what actually happened, not what should have happened. All right, guys, questions on the definitions? Okay, here we go. Let's take a look at some examples. So, in your book, go ahead and go to page 724. All right, here we go. On page 724, problem number 1, let's close read that. It says a coin is tossed 50 times and it on heads 28 times. Find the experimental probability and the probability of the coin landing on heads. Then compare the experimental and theoretical probabilities. So here's what we're going to do. Step 1. All right, let's go ahead. Let's go ahead and find, I just kind of abbreviated there, the theoretical probability first. Basically, we're just going to do what we did in the last lesson. Okay? So when you're flipping a coin, it says the coin is tossed 50 times. Well, I tell you what, in this case, we'll ignore that for a second. Let's keep it simple. All right? Let's just say, looking at the coin in theory, there's two possible outcomes, right? A heads or tails, two sides. And the favorable outcome, it says, is landing on heads, so it's on one side. Now here's what I want you to do. We'll call this step star. Now what we're about to do, we can get another fraction, okay, in just a bit, but when it comes to experimental probability, but you've got to compare them. So you have two choices. Either you can find fractions with common denominators, or probably more than likely, it's a little easier because you have to compare apples with apples and oranges with oranges. Okay? If I say, oh, it's 1/2 versus something happening as, 17 over 38. You say, well, I don't know, Mr. Wilkins, which one's bigger, which one's smaller. It's because they don't look the same. All right? You've got to make them look the same. And that's what step star is. So we need to find either common denominators or change them to a percent. All right? And because we've already been doing that, and I'm okay with either one, but you'll probably want to change them to a percent to be able to compare them. All right? So in this case, 1 divided by 2 is 0.50. Move the decimal over 2 times. Of course, right? 1/2 is 50%. Now comes what we'll call step 2. And that is, let's go ahead and do the experimental probability. This is, remember, what actually happened. So, on here it says the coin is tossed 50 times. That's the possible outcomes, right? Number of possible outcomes, 50. But it says it landed on heads 28 times. I'm going to go ahead and change that now to a percent where we can compare them. So 28 divided by 50 equals 0.56. Move that over. It's 56% chance of it happening. Okay? On here, guys, you're not going to do an experiment. They're actually going to already have the results to the experiment ready for you. Okay, so here's what we're going to do next. Step 3. If you reread the problem, it says compare the experimental and theoretical probabilities. So, if we do that, you would say you're just writing a sentence. The theoretical probability is 50%, while the experimental probability is 56%. And that's all they're asking the first time around. They're actually pretty close to each other. 50%, 56%, very, very close. It's not like one's 50% and one is 90% chance of happening. Okay, what I wanted to talk about though is do they always match up this closely? No. Okay? When they don't, what can cause them not matching up? So for example, right, if you're flipping a coin, realistically you should flip like heads. If you flip the coin 10 times, you should flip heads probably 5 out of the 10 times, half the time. But there could be times where you flip the coin and heads comes up 9 out of 10 times. Now it's kind of rare, but it sometimes happens because it's random. And you're like, whoa, that's really weird. Well, yeah. But with numbers, with probability, there are what they call like streaks. That's why when some people say, oh, you're lucky. Well, you're probably just describing the fact that you flipped heads 9 out of 10 times. And that is kind of lucky in a way because it doesn't fit the probability of it happening. Okay? So, what can cause that? Well, because of the streaks, there's not enough trials. The more trials you have, so if I flip the coin 1,000 times, there's a good chance that head's going to pop up a little closer to 500 times. Okay, because heads might go on a streak, tails may go on a streak of popping up. And then in the end, it will kind of level itself out the more flips there are. That's what it means by trials. All right, so here's what I want to do. Kind of going along with that maybe, but let's take a look on 725. Let's look at problem 3B. 3B. Now it says, the frequency table shows the results of a survey of 70 zoo visitors who were asked to name their favorite animal exhibit. So 70 people came into the zoo. If you take a look at 3B, it says, suppose 720 people visited the zoo, right? Which is a little different than only 70. It's over 10 times the amount of people. It says, predict how many people will choose the penguin exhibit as their favorite. There's that word, favorite, favorable outcome. So here's what we're going to do. On a problem like this, you're going to use the probability, the basic probability, to predict what could actually be if there's more outcomes. So for example, we're going to call this step 1. Okay? And that is, let's go ahead and let's write our theoretical probability. All right? So with that, I don't even know if you'd actually, this isn't even really theoretical, right? Because it actually happened. This was an experimental probability that happened. 70 people came in, they asked, what is your favorite exhibit? So possible outcomes was 70, right? Because there are 70 people. But remember, in part B, it says predict how many people will choose the penguin. Well, the penguin's the favorable outcome. So out of the 70, how many chose penguin according to the chart? Yeah, right? According to the chart, the tally marks, 13 chose penguins. 13 out of 70. Now, remember, this is possible outcomes. That's favorable outcomes. So, here's what we're going to do. Step 2. It's been a little while. We're going to set up a proportion. An equal ratio, equivalent ratio, right? That's what a proportion is. Like an equal fraction. Now, remember, setting up a proportion, you have to keep the same, basically kind of the same idea, or same units, I called it, side by side. Remember, this is possible outcomes, but there weren't 70 people. In 3b, it says suppose there's 720 people. That's what's going on the bottom. Not 720 favorable outcomes, right, that chose penguin. It's how many total customers there were at the zoo. That's what 70 was. We're going to use this as if there were 720. Now comes step 4, and we're going to solve this. Now, it's been a little while. If this was 700, it'd be nice and easy. 70 times 10, right, is 700. But that's not the case. So I'm going to go ahead and I'm going to use cross products. So, remember this. This times this is equal to that times that. So, I'm going to go ahead and write that down. 13 times 720 equals 70 times x. And now we have an equation. So, with the equation, I'm going to go ahead and simplify. 720 times 13 equals 9,360. And that is equal to 70x. And to find out what x is, which is our whole goal, I'm going to divide by 70 on both sides. Isolating the variable. So 9,360 divided by 70 equals, and I get this long decimal, 133.714285. Okay? Listen, it's just asking, you can't have a decimal amount of people. So what we're going to do is we're going to round. 7 makes the 3 go up to 134. So here's what you're going to do. We'll call this step 5, and that is, let's make this into a phrase. Because it's estimated, I'm going to use the word about 134 people. If you want to make it even better, you'd say about 134 people prefer penguins, okay? Or prefer the penguin exhibit. So you use your experimental probability that they give you in that problem. You set up your proportion. When you fill in the number, make sure you're careful, put it on the correct spot, and then solve your proportion. You'll get your answer. Okay, questions on this problem? Okay, so theoretical versus experimental probability.